Biomimicry, you're hearing that a lot. This is what our soil testing is about. We're trying to mimic nature in the lab as best we can. This is an aerial shot of our research fields. See both sides. So these are about 100 acres each. So it's no-till, conventional till, no-till, conventional till. So we took that with our drone. I'm kidding, we don't have a drone. But we're only using cover crops. And since we got hooked up with Ray and them, we're using mixed species cover crops. Of course, we're doing a lot of soil testing and trying to understand what's happening, but it's really a neat study. All right, my wife made this slide. Y'all love this. I don't know what statement she's making here because it says lab technician set for girls, but she put that in there. But we treat the soil as a non-living, non-integrated system. Now, is that reality? No. We focus on physical and chemical. Is that all there is to it? No. We ignore the biological, we extract soil chemistry that soil never sees, and we measure the house and not the food. There's nothing wrong with measuring the house, but the food's more important, and I'll show you why. How can we do it? We can treat it as a living integrated system. Use some new indicators. Nature, chemistry, biology. Physical's important, but we've put so much focus on physical and chemical and ignored the biological. It's time to bring the biological to the forefront. And this is another key. Integrate the data, integration of the data, right? We measure one thing in soil testing and we say this or that. Well, not one thing ever happens in soil. There's just not one thing just doesn't happen. It's an integrated thing. Lots of things impact these things. We're trying to bridge that gap a little bit. All right, to give you context, like these two did such a good job of, these are the Magruder plots from Oklahoma State. That is only 70 years of data, only. 70 years of data. The average is 40% from fertilizer. So if you add fertilizer, 40% of it gets into the crop on average. 50, it jumps around a little bit. So does that not give you a blaring question? Does that not stimulate your mind to go, where's the rest of it coming from? It did mine. Where's the rest of it coming from? We've known this for 70 years. And why did we not address it? Well, it might be hard to do. That's pretty strong data. Here's the Morrow plots in Illinois. This is corn. Fertilizer, lime, fertility average is 57%. Well, where'd the other 43% come from? I have a lot of colleagues that give these tests and they do these fertility tests and they'll say, well, we grew 300 bushel corn at our high rate of fertilizer. And I said, well, what'd the control make? Well, 220. How's that not the story? How's that not the story? How'd you raise 220 bushel corn, no fertilizer? How? Those questions are just not answered. So I took and Dave's deal, and you see how I notice how I moved that off of it?
Why'd your wife do that?
Yeah, why did I do that? I did that.
Oh, you did.
Smarty pants here, why'd your wife do that? I can do things. 2 million pounds of soil on 6 inches, 40,000 pounds of organic carbon. These are rough numbers, don't pin me on it. 4,000 pounds of organic nitrogen, 2,000 pounds of organic phosphate. These are huge numbers. These are huge pools that we don't have access to. Why? Because they're disconnected from it. You feed them, they'll go get that, right? You give me money, I'll go get that. That's giving them money. Feeding them the right food gives them money, and they get involved, and that moves in here, and you got the system running now. Right now, we're disconnected from those pools. Where does that other nitrogen and phosphate come from that fertilizers don't account for? Right there. Right there. But you got to get these guys going to get it. We can do this. We can do this. We can grow this microbial and organic chemical diversity. Jill did a great job of showing all that root exudates. And this is my new slogan. I'm going to make t-shirts. Plants fix dirt. You can't fix dirt with chemistry. You fix it with plants. If you put chemicals out there, which is, I'm not against that, I'm just saying, you could put chemicals out there and address a problem. But if you want to fix it, I mean really fix it, plants do that because they're living and they respond to stimuli. Chemicals don't do that. Plants do that. And there they are. Jill went over all this. So here's the nitrogen cycle. All this is to show this is a really, really complex system, all kinds of above and below ground stuff happening. And here's what our current testing, soil testing, that we measure that. Nitrate, nitrogen. One form of nitrogen with 2 molar KCl, which is highly super duper concentrated. Soil never sees that. And that started in 1965, and we're still doing it today. 1965. Can we do better? You betcha. This is what we measure for nitrogen. This is ammonium nitrate. We extract the soil with water because it rains water. Come on, somebody giggle, because I had to have that conversation with some scientists. What do you mean? We got to use this chemistry? No, it rains water. Let's extract it with what the soil sees. So we measure all these things to get at the nitrogen number. Here it is, phosphate, the black box of soil nutrients. Lots of things happening, lots of things going on, lots of things we don't know. So for phosphate, you can use a couple of different instruments and up to 7 different soil extractants, depending on what lab you use. And most of them don't tell you because, nobody asked. But the reason we get all these different phosphate numbers is because everybody's using a different method. This is what we measure for phosphate. All this. There's a soil extractant I developed that mimics plant roots that Jill was talking about. We're trying to, the question was, well, what does the plant see? What does the soil see? Well, it sees these things. Soil health, there's these, boy, here we are. In the 80s, soil quality was the big issue. Does anybody remember that? Soil quality. You know what we did? We argued about how to define it for 20 years. That's the truth. This is why I like soil health. That's not something you need to argue about. Everybody gets that. So there's these tests. Permanganate, it's active carbon. It's an okay test. It's probably a better estimate of organic matter, but it's not what the microbes see. They don't see permanganate. Organic matter is a great measurement, but that's the house and not the food. There's other tests that take quite a while. They can't measure everything they need to, take up to a week. None of this is field conditions. This is what we measure. We use this Solvita test, which is microbial activity. There's your food. Water-soluble organic carbon, water-soluble organic nitrogen, the balance of those two things. So activity, food, balance. Then we give you a score and a cover crop suggestion. So these are the traditional methods, NPK, soil pH, CEC. We don't do that. We don't measure that. We don't measure that. We don't measure that. We do those things. Where's the soil biology? This is, I threw this one in there, not my wife, me. These are some of the chemistry that we use in the lab currently. Sulfuric acid, these are nasty. You don't want these on you. These will hurt you. This is what we do. And I have guys that ask me about anhydrous ammonia. Y'all know about anhydrous ammonia, right? Cheapest form of nitrogen fertilizer, right? Wrong, not true, but we don't have to get into that right now. But a farmer asked me, he said, well, now is it bad for the soil? I said, well, next time you're putting anhydrous out, pull the hose off and shoot it on your arm. I had a friend of mine do that accidentally. He didn't on purpose, even though he's from Oklahoma like I am. But it burned him bad, 3rd degree. What do you think it's doing to the soil? When we put fertilizer out, not anti-fertilizer, anti-too much fertilizer, we'll get that on record. when we put, you got these fertilizer rigs running around, right? Have stainless steel tubes and stuff, right? And they corrode. Well, wow. What do you think that's doing to the soil is the point. The soil's alive. We don't treat it like it's alive. So anyway, here's all these things, and this is what we use. Water and my extractant, that's it. So I'm going to give you a quick history lesson just to show you that this is not something new that we just made up. This was happening in 1896, 1919, 1924. These are Russians, way ahead of us. 34, 35. CO2 evolution was the greatest. That's the first day after rewetting dried soil. 1935. I brought that back. Brought it back. This is what we do. These guys, they were on it. They were getting there. CO2 evolution. Flush of carbon and nitrogen from rewetting dried soils. Biological, yeah. It's not chemical. Biological. That's important. 1956, we knew these things. And then in 1970, we said, no, we don't need to worry about activity. We can measure biomass. Whoops, went right off the rails and didn't know it. Okay, this is back in 94. I was 40-something, I don't know. I was late in grad school. But we started seeing that this little bump, you see there? This is time and days. That's 24 hours. CO2 evolution. Poor soil, better, best. See how the bump gets bigger and bigger as the soil gets more fertile? Can't be that simple, can it? Can't be. Yes, it is. It is that simple. Nature's been doing this for a long time. And we saw this in the lab, and nobody believed us. And we wrote a bunch of research papers before people started finally accepting it, just because we wouldn't shut up. And today, and so the fun, because, you know, I thought that this was going to be revolutionize everything. And this is 94, right? And here we are today. So 20 years later, yeah, that's how naive I am. So this is a company in Maine. I had a method. They had this little gel paddle right here that you put in a jar and you take it out. You put it in there and push that button and it gives you the CO2 from that soil for 24 hours. Awesome. Combination of technology and methods. Here's the hard part to swallow, though. This was the federal government hooking up with private industry to produce a product to help farmers. Huh? Let that soak in. Anyway, so what we're doing, what we're kind of doing different, to sum up pretty quickly, is we're asking the soil these questions. We're not beating it up in the lab. We're asking it, what's your condition? Are you in balance? And what can we do to help? You tell us. Let the soil tell us what's happening, not the other way around. Soil biology is a complex, integrated living system. We can't say that enough. That organic carbon and water drives the system. That's what they're after. Microbes take in O2, release CO2. That's what we're measuring. They've been doing, our plants and dirt has been doing R&D for millions and millions of years, or thousands of years, depending on your religion. Wow. All right, so soil organic matter is the house. That's an okay thing to measure, but you can have a big house with no food, and what have you gained? You know, but it does trickle down. They are linked, but the association's a little loose at some point. This is what they're after. This is the food. See, there's the carbon, the nitrogen, the phosphate. This is water-soluble organic right here. This is where they live. This is where they work. This is what they go after. And that's what we're measuring. We're not measuring the house. We're measuring the food. And we're talking about 12,000 part per million carbon for soil organic matter measurement. We're looking at 1 to 300 part per million. So we're looking at the tiny food source. And to give you an example of that, this is converted to organic matter. You see this, Maine, Wyoming, Idaho, Texas. Willie, we don't like this, do we? This makes us look bad. See, that's a nice stair step. Yeah. This is the same soil now, all the same. See, there's a nice stair step. But when we do the water extractable, it doesn't follow it, does it? And when we do the microbial, does that look like that? No, that looks like that. That's the food. That's not the food. This is not alive. This kind of is because they're acting on it. The other thing we do, we have total nitrogen, water extractable, and we break that apart for you. We measure inorganic and organic. So we have inorganic in and organic in, the water extractable. We've never seen this before because we didn't have the technology in the lab to do it, but we do now. This pool, there's your missing link right there. We haven't been able to measure that, and that's where that nitrogen's coming from. There's another pool in here that feeds that one, this water-soluble pool. Don't really know what it is yet. But it's there, and we're going to find it someday. We're not going to give up on it. We're going to find it. Here's that huge storehouse. When we get this system going, you get the microbes going, they start feeding that pool, it feeds that pool, it feeds that pool, it feeds the plants. These are some of the compounds. Jill showed some of this. We're learning a lot. These plant roots, again, like Jill was saying, can put proteases out. They can break this stuff down. I mean, there's a whole system out there we're unaware of. So the point of this thing is, does anybody see just nitrate nitrogen on there? No. It's a very complex system that we're only now beginning to understand. We've only been missing half the nitrogen. That's all. Yeah. Only half. We ran 6,200 samples through our lab last year, and this was the average. 36 pounds of inorganic nitrogen, 34 pounds of organic nitrogen. There's what we're missing. That's why. And then my wife has to jump in there. I should let Ray tell this story, but we were sitting there talking to a bunch of farmers. My wife was there, and they were like, well, can plants take up organic compounds? And I was like, well, yeah, and here's the reason. That's because I'm so brilliant, like Gabe said. I'm going to launch into this conversation. My wife goes, well, I guess herbicides wouldn't work if they couldn't, would they? And all the farmers go, yeah, she's right. It was over. It was it. So I put her up here and quoted it. Anyway, then she put that in there. Plants eat inorganic in and organic in. For me, I guess. I don't know. We also, so seed-in ratio. As the seed-in ratio drops, we get more organic N and P, and vice versa. If this one goes up, that one comes down. So there's a balance. There's a teeter-totter. We have a soil health calculation that uses a bunch of the measurements, so we integrate that data together to give you a number. NRCS likes their number, so we gave them a number, but it's a good number. It works. It's 5 things put together. So here's the new kind of paradigm. We're soil testing and nature's image. So we're measuring that and that and that and that. Now we're getting there. Now we're starting to get there. And then we integrate all that data together. This is all interconnected, so we analyze it that way. I'm going to go through this real quick. Most folks think you take some dirt, you put it in a machine, and out comes the answers. It doesn't work that way. We put it, each sample gets 4 grams in there, 4 grams in there, 40 grams in there. Then we hit it with our soil extractant and water. And, you know, we've been using these highly disruptive acidic and alkali solutions and calling it plant available, and that's just never been right. But it's what we've accepted. It's just, you know, this is a complex thing that Jill pointed out, that root exudates drive this system. So then we beat it up a little bit, we shake it for 10 minutes, and then we centrifuge it for 5 minutes, and then that's what we pour that in through a filter paper, and that's what we analyze right there. This is a carbon nitrogen analyzer. In 07, we got that component right there. We've had this one for years, for a long time, but that's the nitrogen component right there, so we can do total organic carbon and total nitrogen on every sample simultaneously. So that's that machine. That machine had to come along to make this all work together. And then we have inorganic N and P, but we use both extractants, both mine and water, on this machine. And then the ICP just gets my extractant for calcium, phosphate, potassium, iron, aluminum. This is the microbial activity stuff. There's the water coming in, oxygen. They give off CO2. We can monitor CO2 levels in here and tell about how many people are in here because we're all giving off CO2. It's the same system. It's the same system. So, really complex stuff. We put water in there. We drill holes in the bottom of this jar, and we drop it in there. Capillary action will re-wet that right where it needs to be, whatever that soil's capability is. I had to write a paper on this, but it works really well. That had to come together. Put the paddle in there, put it in the incubator, out it comes, you know, went through that. We didn't make this up yesterday. We've been at this for a while, so there's plenty of publications to look up if you want. This is on the web. We unfortunately call this the Soil Nutrient Assessment Program, so a lot of people think it's food stamps, but it's not. This is on the web, and you can put your state and county in there and all that. And all this tool is designed to do is to show you this is your chance of hitting your yield goal. This is, we farmers that I've known and worked for most of my life fertilize for maximum yield every year. Every year. Is that realistic? No. So anyway, if you look at this is for 200 acres and a 50 bushel yield goal. I think this is us. Yeah, Bell County, Texas. Look at the chances that I got of hitting that yield. None. 0. But by God, I'm going to fertilize for it, just in case. Well, here's what happens. Well, let me go back. Okay, and it's going to cost you $4,200 on that. Now, what if we drop it back to 35 bushel? Just fertilize to make 35 bushel. Now we're getting somewhere, right? Fertilizer input's way down. Now we got a chance. And just because you fertilize for 35 bushel doesn't make it won't make 40 or 45 if it rains. We figured that out through extensive research and billions of dollars that if it rains, it doesn't matter. Doesn't rain, doesn't matter. So the results, we use an Excel file. It gives you your plant available NPK and a little fertilizer calculator and this information. These are the boys that are doing the work. I used to do all the work, and then I got these 2 years ago. So if the quality's gone up, that's because I quit doing all the lab analysis. So now these guys really work hard and do a good job. Couldn't do it without them. That's the web tool address right there. How am I doing? Time. Okay, I'm going to switch this to I'm going to show you the output file if I can. You can get that web address from me later or something. All right. This is what we send. Well, we're working on this. I'm working on this. Okay, my wife made it, but I'm working on it. This is what we send this is what we send out right now. So there's your NPK. This is already converted to fertilizer speak. So here's your pounds N, pounds P2O5, pounds K2O per acre. And then we take current fertilizer prices times those numbers and give you that column right there. So that's what the fertility's worth in your soil right now. Not what you need, what you have. But in $1 per acre, that's a neat number to see. And then here's our little run calculator. I've already put corn on it and everything just to make it easy. And you hit that little button right there. Once you put your, there's different ones. There's a pop-up menu right here. But you hit that run calculator and then it spits out. Here's what you need. So there's your fertilizer needed if you're going to grow this corn. And then it goes on to the right. And so here's, if you just did nitrate only, which is what most labs do, so that gives you that number. But this is what we find in addition to it, using the new methods. And then this is the dollars per acre saved in nitrogen. That's a neat, so that's a nice. People want to see that. Because there's 3 commercial labs that are offering this test right now in the U.S., and it's about $50 to $55 a sample, and farmers are like, oh my God, no, that's crazy. I can get it for 10. It's like, yeah, you can get crap for 10, but good luck to you. We can do better, and it's going to cost you a little bit more. We know these things, but my point is this, because a guy called me, he said, that's ridiculous. We're not going to pay $50 a sample to get that done. We pulled a sample up, and I think he was right in this area. $13 an acre saved him just in nitrogen. Now how expensive was that test? He had 1,000 acres. I said, so $55 is too much to save you $13,000. He goes, well, I guess I'd be an idiot if you put it like that, wouldn't I? I love farmers, man. They just. But he hasn't thought about it like that because he hadn't had to think about it like that. You just go, you give your fertilizer guy, you take a soil sample and put out the fertilizer, and I'll write you a check. And what Gabe say? Those guys are signing the front of the check, folks, not the back. So we can do better. We can do better. This is not the end all either. This in 10 years, hopefully somebody else is standing up here with a better set of tests than I've got. And then so here's the microbial activity. There's the organic carbon, organic nitrogen, the C/N ratio. Here's your soil calculation. We want to see that number over 7, but it's it's relative. Here's the cover crop mix. It suggests that your soil's telling us it wants. If it says 50-50, 50 legume, 50% grass, that means you're in good shape, by and large. If you're not doing so good, if you see these some of these drop back, it's asking for more legumes because carbon and nitrogen really good. And then we break down the total nitrogen, the inorganic and organic and phosphate the same. But here's what we're going to go to next. We're going to have this it's going to look just like this. It's going to have a little tab that says graph it. And you can just go through here and click on the sample and click graph it. And so it's just a graphic way to see the information a little bit better. And it's neat though, because if you take that sample right there, here's the nitrogen, is how the nitrogen's broken out. So there's more organic nitrogen than inorganic. We want to see that. That's what we want to see. We don't want to see this flip the other way. So it's really nice because once we start to do a better job of educating folks about what all this stuff means, then they can just glance. It's like, okay, we got more organic than inorganic. That's good. We got more inorganic phosphate than inorganic. That's good. We don't see that very often. So we're going to start moving into this a little bit better interactive data. And then we go on down. There's just a lot of stuff, but okay, that's all I have.